Normal distribution, also known as the Gaussian distribution, is a probability distribution that is symmetric about the mean, showing that the data near the mean are more frequent in occurrence than data far from the mean. In graph form, normal distribution will appear as a bell curve. The normal distribution bell curve. Real-life situations that will produce a normal distribution bell curve are height, tossing a coin, IQ, returns from the stock market, shoe sizes, birth weight. Normal distribution has a single peak, with most of the values around the mean. The distribution is symmetrical, with half the values above the mean and half the values below the mean. It tapers out in both directions, because the further you get away from the mean, the fewer values there are. The 68, 95, 99.7 rule. The normal distribution is perfectly symmetrical around the mean. In fact, 99.7% of the data is within 3 standard deviations above or below the mean. In fact, 68% of the data under a normal distribution curve lies between -1 and +1 standard deviation from the mean. 95% of all the data under the normal distribution curve lies between -2 and +2 standard deviations away from the mean, and 99.7% of all the data under the standard deviation curve is between -3 standard deviations and +3 standard deviations away from the mean. Normal distributions are written such that x belongs to the normal distribution with a mean mu and a variance sigma squared. Example 1. A competency test has a mean mu equal to 80 and a standard deviation sigma equal to 10. A. Sketch the distribution. Draw a normal distribution bell curve and put in the mean. The mean is equal to 80. Then you can put in 3 standard deviations above and below and add their values. The standard deviation is 10. So above would go 90, 100, 110. Below would go 70, 60, 50. Write the standard deviation by the side. So sigma equals 10. B. Between what two scores does the middle 68% lie? Well, the middle 68% lies between -1 standard deviation and 1 standard deviation. So those two scores in this case are 70 and 90. So the middle 68% lie between 70 and 90. Between what two scores does the middle 99.7% lie? Well, the 99.7% lies between 3 standard deviations below the mean and 3 standard deviations above the mean. In this example, it is between 50, which is 3 standard deviations below the mean, and 110, which is 3 standard deviations above the mean. D. To be in the top 2.5%, what score must you get? Well, to be in the top 2.5%, that is above 2 standard deviations above the mean. In this case, 2 standard deviations above the mean is 100. So in order to be in the top 2.5%, you must get a score greater than or equal to 100. Example 2. In the army, the head circumference of the soldiers is normally distributed with mu equal to 22.8 and sigma equal to 1.1. A. Sketch the distribution. Draw in the mean, which is 22.8. Write down the standard deviation, which is 1.1. Draw in the 3 standard deviations above and below the mean and put in the values. So adding 1.1, so that is 23.9, 25, 26.1. Subtracting 1.1 from the mean will give 21.7, 20.6 and 19.5. 23.9 is 1 standard deviation above the mean. That means it is 34% of the data above the mean. The mean is 50%, therefore it is 50% plus 34%, therefore 84% of all soldiers have a circumference greater than 23.9 inches. C. What percentage of soldiers have a circumference between 21.7 and 23.9 inches? If you look at the distribution, that is between 1 standard deviation below the mean and 1 standard deviation above the mean. Therefore, 68% have a circumference between 21.7 and 23.9 inches. D. What percentage have a circumference above 26.1 inches? If you look at the distribution, 26.1 is at 3 standard deviations above the mean. Between minus 3 standard deviations and 3 standard deviation lies 99.7% of all the data. Therefore, above 3 standard deviations is equal to 0.3% divided by 2, which is 0.15% of all the soldiers. Normal distribution on a GDC. Example 3. A journey, T, is normally distributed with mean 31 and standard deviation 5. Find the probability A that T is greater than 31. First, draw yourself a diagram. The mean is 31. That means that 50% of all the values are greater than or equal to 51. So the probability that T is greater than or equal to 31 is 0.5. B. the probability that T is between 29 and 32. Again, start with a diagram. Mean of 31, and we want between 29 and 32. So we want the shaded area. We can do this on a GDC. So on the GDC we do a normal CDF with a lower bound of 29, an upper bound of 32. Mu, the mean, is 31. Sigma, the standard deviation, is 5. And that will give a probability that T is between 29 and 32 of 0.235 to 3 significant figures. And C, the probability that T is less than 36. Again, start with a diagram. Mean of 31. We want less than 36. So we want all this shaded area. Again, we use a normal CDF. Lower bound 10 to the power of minus 999, which is a very small number. Upper bound 36. Mu, which is our mean, is 31. Sigma, which is our standard deviation, is 5, which gives us the probability that T is less than 36 is equal to 0.841 to 3 significant figures. Finding the value that gives a certain probability. Example 4. Melons are normally distributed with a mean of 972 grams and standard deviation of 42 grams. The heaviest 6% are classed as overweight. Find the weight above which the melons are classed as overweight. First, draw a diagram to represent the information given. The mean is 972 and the standard deviation is equal to 42. We want to find the value A, whereas the top 6% are overweight. If the top 6% are overweight, 94% are not overweight. So we want to find the probability that the weight W is less than A is equal to 0.94, which is 94%. We can do that on a GDC. We use the inverse normal function on the GDC. Our area is 0.94. The mean, mu, is 972. The standard deviation, sigma, is 42. That gives us a value of A of 1037.3 grams. That means 6% of the melons are above 1037.3 grams